In a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice? A flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this illusion.
Mostly these guys talking, and I'm just facilitating. It's about an observation that Dr. Mike Heffron pioneered, and he's in the upper right of the screen there. Anyway, I'll let them introduce themselves. Whoever wants to go first, go right ahead.
Awesome.
Go for it, Alan.
All right, thank you, sir. I am Alan. I'm here from the YouTube channel Space Audits. I am going to be discussing the celestial theodolite, which is a concept which involves using timing intervals to measure elevation angles to confirm the physical elevation angle of a mountain peak. This method was presented by Dr. Mike Heffron. I've been arguing it and presenting it to people. Jesse here has taken it, has participated in the measurements and the methodology now. So we have some difference in measurements for comparison. So Mike here is going to facilitate a conversation here between us all where we discuss the method, the measurements, and the new measurements that Jesse put forward. I think that kind of sums it up.
Dr. Mike.
Sorry about that delay. I have to remember to unmute, and I'm gonna go try to kill the audio. I've got a second audio feed in my ear. All right, hopefully you can hear me.
Yep.
Yes.
I'm Dr. Michael Heffron. I'm just a mere ordinary member of the Aether cosmology group. And I came up with the concept of the celestial theodolite back at the end of January this year. So it's 17 weeks old this week. We're still in the infancy of figuring out what's happening.
All right. And Jesse.
Well, I found this rather interesting and started exploring it more. And when I looked at how it worked, it looked to me like it could be used to get flat Earth results, concave Earth results, or globe Earth results, or anything between flat and concave, or globe and concave. So once the weather cooperated and my schedule cooperated, I went out and filmed some stars rising over a mountain that matched, using this method, matched the globe Earth.
All right.
All right, awesome.
Proceed.
If I can screen share, I will do a quick recap of the methodology, and then Mike can get into the work that he contributed applying that method. All right, just trying to figure out how to screen share. Use system desktop. That sounds reasonable. Everything working accordingly?
Looks good.
All right, awesome. So the basic concept for the celestial theodolite is suppose you have an observer X distance away from some mountain peak, right? Well, you can figure out two things about that mountain peak, right? You can know your difference in elevation between the two, and you can know the distance between you and the mountain peak. Using that, you can apply the old Pythagoras theorem to derive what the angle would be for that mountain peak, assuming planar geometry. Then, of course, you could subtract 8 inches per mile squared off the difference of that to get the difference in elevation for what the globe would predict as the physical elevation peak. Because as we all know, on a flat Earth, the elevation of the peak is not going to be physically reduced because there's no Earth curvature to cause it to be tilted away from you. It would be an optical effect if it appeared to be lower than what it actually physically is. And on a globe, it would be physically at an angle. So it's going to be lower in the horizon, like as a function of its physical elevation to you. So what we do with this angle that we calculate based off of this relative distance away from some peak, we then go into Stellarium, right? And we reference that peak, and we aim our crosshairs at that angle, and then we just wait for stars to intersect with that angle. We write down the star names and the times in which they're aligned with that angle. And then we go back to our spot where we did our initial calculation from, and we observe said mountain peak. And when these stars intersect with that mountain peak, if we no longer see them, we know that they are occluded by a physical object. And based off of that timing, we can relate that to the angle. So we could show geometrically that alpha here would be equal to alpha here if the timing that you no longer see the star corresponds to the same thing. Now, quick note on Stellarium, the way that we're using it, we are turning off refraction, which reverts it to its geocentric coordinates, which is like an idealized position of where the quote unquote true position of the star, whereas the refracted position would be, where you visibly see it, and then where you would actually have to apply additional corrections to move that star position to where you would be able to use it for cell nav and stuff like that. But so that's the distinction between what we're referencing here, the true geometric position versus the apparent position. So when we're referencing this occlusion timing and the angles corresponding, we're only concerned with the true geometric position and when we no longer see the star. Okay, so that's the basic outline for everything. And so basically, if the Earth were a globe, then these timings, it would take longer for the star to get into the horizon because it has to get lower to actually physically occlude that peak. So we have two mutually exclusive outcomes here. And I think that kind of wraps up the process and the methodology here. So we can, so Mike has a spreadsheet here of different distances and mountain peaks that he used at different occlusion timings. So I'll go ahead and let him go over those. Mike, if you want to screen share to go over it, or if you just want me to scroll down and go and like narrate the data or whatever, we can do that. It's up to you.
Yeah, actually, if you could screen share and narrate, that'll probably be easier. I've never, well, this is my first time on Zoom ever, and I'm not sure I can screen share without painting myself into a corner I can't get out of.
No worries. No worries. Okay, so if you can see the screen up, I have your data set up.
Yeah.
Can you see that, Mike?
Okay, I can see the data.
All right.
And I'm having to look at a bigger monitor that's above me. So if you see me looking up, that's what I'm doing.
No worries. No worries. Okay, so we got your initial measurements here. Oops, all the way up at the top, starting from Pikes Peak. You just want to go over a couple of these distances and elevations, and then the significance of the table assessment on the side here, what we've done or what you've done.
Okay, very good. And so for the spreadsheet to make sense, it's important to know how I did this. And I got these measurements by pointing a C-star S50 telescope at Pikes Peak, or well, at each of the peaks. This particular peak is Pikes Peak. And I put that on a 1 second exposure, 1 second per frame time lapse. So basically it's keeping the shutter open for 1 second and then moving on to the next frame over and over and over again. The gain is turned up all the way up on maximum on the telescope, so I can see as many details as possible. And the date in the leftmost column, right under the observer label, that's the date of the video. The next column to the right is the time that the video began. The next column to the right of that is the frame number of the video. The next column is how many seconds per frame. When we get down a little ways for 1 day, I was using 2-second frames. And that was the last time I ever did that, because I realized I needed to do it 1 second to be able to see the data more clearly. So the next column to the right of the frame count, the seconds per frame, is the calculated time of the frame number of seconds plus the start time equals this time that the star was actually occluded. The column to the right of that is the actual star that we're seeing occluded by that frame. And that's under the column that says star all the way at the top. And the next row down says that was Pikes Peak. The next row down is the distance to Pikes Peak from the observer, which is 50.7 kilometers from my house relative to Pikes Peak. The next column over is the magnitude of the star. And that's just so that helped me identify the stars in some cases where there was a little doubt. The column just to the right of that is the actual azimuth of the star according to stellarium as observed on the mountaintop. The next column to the right of that is the elevation of the star relative to the peak. And the reason for that is I should probably talk a little bit about hypothesis testing. This is all part of an experiment I began with the hypothesis that the Earth is a globe, and with the hypothesis that the Earth is a globe, people who've studied hypothesis testing will tell you it's impossible to ever prove a hypothesis. So what you do instead is you reject a null hypothesis, which is the opposite of your hypothesis. And it has to be not only opposite, but mutually exclusive. So if the hypothesis is the Earth is a globe, my null hypothesis was the Earth is not a globe. And if the Earth is a globe, it cannot be not a globe. If the Earth is not a globe, it can't be is a globe. And so what I want to do, the goal of hypothesis testing is reject the null hypothesis. So I want to reject the contention that the Earth is not a globe. And if I can reject it, then I have a quantifiable level of confidence that the Earth is a globe. So that's what I set out to do. And that's why this is constructed in such a weird way. So the celestial theodolite concept I came up with to demonstrate that the Earth is not a globe is my reasoning was if the Earth is a globe, then the Earth between me and the peak is flat. And if the Earth between me and the peak is flat, then I should be able to use plane trigonometry to determine that the 2,226 meter rise of Pikes Peak above my altitude over that distance of 50.7 kilometers is the equivalent of a 2.5 degree angle. In fact, this says 2 degrees 30 minutes and I think that says 31 arc seconds. That's a little fuzzy for me.
51, but yeah.
On this. Okay, so if the Earth were perfectly flat, that's the angle I'm expecting from my house to Pikes Peak. And so if the Earth is flat, then when the peak occludes that star at that angle from my house, that should be the exact angle that a viewer on the peak would see that same star. And so what I'm measuring here is I tell Stellarium I'm on that peak. I tell it what time I saw the star occluded, and ask Stellarium what is the elevation of that star, and that's what's recorded in this highlighted column, column I, which is the Stellarium indicated true elevation of the star. This is with atmospheric correction turned off. In other words, this is where the nautical almanac says that star actually is. The next few columns just convert that degree minute second nomenclature to separate degrees, minutes and seconds. And that's so I can reassemble it into a decimal degree in the next column to the right. And then so one more column to the right. And this is the indicated rise of the occluded star at the angle from my house that is indicated by Stellarium. And then and that's computed by the degree angle just to the right of that elevation. So I added this height of the mountain from the plane of the observer to the actual altitude of the observer, which is in column B2. In this case, it's about 2,074 meters. Add those two together and you come up with 4,347 meters and 0.1 meters for that first star. And that's compared to right at the top of that column, it says Pikes Peak is actually 4,299.8 meters above sea level. So, and the next column over basically shows that indication is 47.3 meters too high. So it's a little above predicted. And then if you can scroll over another couple columns, the next column over converts that discrepancy in meters to a discrepancy in arc minutes. And then the column just to the right of that converts the discrepancy in arc minutes to a discrepancy in seconds. So in other words, that's how many seconds difference there should be between when a flat earther would see the star occluded versus when a globe earther would see the star occluded. And then the next few columns are equivalent data for the globe earth using d squared over 2r. Globe earth would expect the indicated altitude to be 201.7 meters lower. And then if you go to the next column, that's the altitude difference in sorry, that's using the angle indicated by Stellarium added to the 201.7 meters. That's how much too high that height would be on a globe earth. And then the next column over, that's the same deviation in arc minutes. and then the column just to the right of that is the same deviation in seconds. So some people like to look at it as meters, some people like to look at it as arc minutes, some like to look at it as seconds. So the spreadsheet just includes all three of those. And then everything else on the spreadsheet are just miscellaneous calculations to help verify the data. So basically, this whole weird layout is so I could easily take captured telescope video frame by frame, identify which frame the star disappeared, get the occlusion time from that, look it up in Stellarium, plug the data in from Stellarium, and see how far off was it from what was expected by both flat Earth and by globe Earth. And then we can compare the two. And there's miscellaneous other there's some averages on here, and there's some standard deviations. And eventually we will have accumulated enough data where we can start using some of those other things. But only 17 weeks into this experiment, we're still basically in data collection phase, and I think we've collected something in the neighborhood of 40 or 50 observations that are recorded on this data sheet, and some others have come in and they haven't made it onto the data sheet yet. So that first mountain we looked at was Pikes Peak. That was the first mountain I ever collected this data for. Next one down is Blodgett Peak, which is over by the Air Force Academy, which is almost straight west from my house, and it's a little closer than Pikes Peak. And you can see on this one there's more deviation. With Pikes Peak, it had a pretty tight cluster of data. There was a little bit more variation on Blodgett Peak, and it wasn't a perfect match for either globe or flat Earth, and that kind of alludes to what Jesse was saying, that you can come up with data to show anything, and so you want to be sure you know what you're looking at and try to figure out where the errors are coming from. But always keep in mind that the premise is what we are looking for is a clear distinction between what flat Earth would predict and what globe Earth would predict. And we're looking for, does the data clearly indicate that it's one or the other, so that we could try to refute the null hypothesis. And I internalized the null hypothesis as the Earth is flat. The real null hypothesis is the Earth is not a globe. And so we want something that clearly refutes that the Earth is not a globe. And for most of this spreadsheet, we are not finding that refutation, so we cannot refute the null hypothesis, and therefore we'd have to come to the conclusion that indeed the Earth is not a globe. For some peaks, the data kind of clearly indicates it's flat. On other peaks, it makes you wonder: is it concave? Is it convex, or some other kind of ellipsoid? If you can scroll near the bottom to the area that has a yellow banner, yeah, that's good. Blinn Mountain is the data as best as I could decipher it from Jesse's video, and that's incredibly close to what a flat Earth would, sorry, a globe Earth. Please excuse me when I say the opposite of what I mean. I do that on occasion because I'm tending to look at things from all different points of view. So
That's okay.
If you catch me saying something backwards, it's okay to challenge me on it. So don't feel bad about doing that, because I know it happens. But for Blinn Mountain, I think the data is much closer to globe Earth than it is to flat. I'm a little concerned about the data because the sample deviation is 38.6 meters. That's the biggest deviation we've had on any collection of data so far. Right above that is Greenhorn Mountain, which was our previous worst, and that mountain's 3 times farther away, and the data was clustered within 20.7 meters of each other for that mountain. So I'm not sure why Blinn Mountain, being a much smaller mountain that's much closer, has such a big deviation, and that's just something we'll have to examine as the days go by to see if we can figure out why is this data all over the place the way it is. But anyway, that's a brief introduction to the spreadsheet, and I'd be happy to answer any questions about it, or we can just go on to other topics as the audience or moderator may wish.
Could I?
Yeah, I think Jesse probably has a response to that.
Yeah, I would
Yeah.
like to show a few things.
Let me
So
stop the screen share real quick. If I disconnect, I'll be right back. It might kick me out. Nope, it was successful. We're good.
okay, let's see. I want to show some of the video that we're working from. And first, I will show some of the excellent time-lapse video that Dr. Heffron gathered. With your kind permission, sir.
Yeah, you're
Sorry,
good.
it took me a while to find mute. Yes, go ahead. Show anything of mine that you wish.
Okay, I think that's it. Are you seeing your video with my red lines overlaid on it?
It looks good.
Okay, so I got this queued up. So this is just an example. This is, I think, the last one you did on Greenhorn Mountain. And there's the reason there's two. Well, so in the beginning, I traced in the horizon line because you could see it in the beginning. So that's where the red line came in from. But then later, as you mentioned, you had to change the angle of the telescope a bit to get a flashing light out of it. So that's why there's two horizon lines. I just copied it down to where the stars were actually getting included. So as you can see, there is a star coming in for a landing and another star and some very recognizable patterns. And you can see they all terminate along that lower red line. So that's a sample of the star occlusion timing video that Dr. Heffron made. Now let me change screen share to one of mine. If I can, let's see here. Does it let me change? Or I guess I stop sharing and then...
You often can, at the top, there's a share this tab instead option. Probably.
Oh, okay. All right, let's see if I can share this one. All right, now you should see something that looks like it's looking through a night vision scope.
Yep.
All right, so you can see there's a radio tower, there's a hill, and then here's a star up here, and then you can see one just rose. And so I was recording in real time because I had a vintage night vision device connected to my telescope, connected to a GoPro with WWV from Fort Collins, the atomic time station, transmitting or playing in the audio. Is the audio coming through? Probably
I
not.
don't hear.
I don't hear anything now.
Doesn't matter. Anyway, so that's how I recorded, assured that I knew what time each frame was, and then I used that to synchronize a timestamp that I overlaid in a video editor. So that's the sample of my video. I did two that night, one from Edith's Hook at 25 miles, 0.4 away, and then one from the old Olympic Highway. It was like, I don't remember, a bit closer, about half as far or something. Anyway, now let me see if I can change to my spreadsheet. New share. Oh, there's a new share button. Oh, I don't need a new share. Oh, yes, I do need a new share.
If it's a different window, you might have to.
Yeah, they're
instead of a
different windows.
tab. Okay.
Okay, I go back to here. Okay, share. All right, now you should see back on the black and the red, right?
Yep.
Yep.
And there. So back before I had an opportunity to film my own star occlusions, I did some analysis on Dr. Heffron's data. But I started from the ground up. I used his, the stars, the time that he reported, and then later I directly extracted the time from his videos, which is what that one for the Greenhorn Mountain was about. And I used his observer location and the target location, and see if I can scroll to the right. But then I did all my own math for distance. I used the extended Haversine formula to automatically calculate the distance, automatically calculate the delta height in feet, predict the globe angle, and predict the flat Earth angle. And then you can put in the method, the results of stellarium from using the method, and then it automatically calculates the altitude in decimal degrees, the altitude angle, based on this DMS input here. And then it shows, let's see, it shows the difference between the Heffron method and the flat Earth prediction, or the globe Earth prediction. So for example, these first two were Pike's Peak. Yep, Pike's Peak. And they were 15.5 arc minutes above the globe Earth prediction and 1.9 or 1.6 arc minutes above the flat Earth prediction. So very close to the flat Earth prediction. But I noticed that the next one, which was Blodgett Peak, and I keyed all those in, actually was closer, all but one, like one of them was closer to flat Earth prediction. The rest were closer to the globe Earth prediction, and the average was closer to the globe Earth prediction. And it was good data. It had a standard deviation of about 25 arc seconds. So that one, it's like when it's halfway between, but slightly closer to globe, it makes you scratch your head. Is this method really working? And if the standard deviation had been really high, it's like, okay, maybe it's just got a lot of noise in the readings, and, but the standard deviation is low, very small compared to the disparity from the flat Earth prediction, which equates to a 168 foot difference from the flat Earth prediction in elevation. So then I did Cheyenne, which was also from I used his times and the star names and observer location and all that stuff from his spreadsheet. But then I calculated my own globe Earth and flat Earth predictions and everything, because I use the same formula in all of these. It's just the flat Earth prediction is simply the arctangent of the rise over the run. And then the globe Earth is that minus 8 inches per mile squared, actually. And so you can see that one was 5.6 arc minutes below flat Earth prediction, but 5.8 arc minutes above globe Earth prediction. So it was about halfway between, but slightly closer to flat Earth. And then the next one was much closer to flat Earth. Mount Rosa was like his best ever. It was like oftentimes less than 1 arc minute from the flat Earth prediction. So that one was really the closest one to the flat Earth. And so then there was Blue Mountain, Green Mountain, and Greenhorn Mountain. Let's see. Let's look at those two. Blue Mountain and Green Mountain were. So Blue Mountain was about 1/3 of the way between. It was definitely closer to flat Earth, but not spot on, but pretty close. Then Green Mountain was very close, almost within an arc minute of flat Earth prediction. The first published data for Greenhorn Mountain was pretty erratic, showing missing 1,035 feet and then an extra 300 feet on 2 stars. But the weather was bad, and so Dr. Heffron went back and got new data. By the way, I was able to identify those stars correctly, and they did actually both give 1988 and 1984 extra feet compared to the globe or the flat Earth. See, I do it too, don't I? Compared to the flat Earth predictions. So then the rest of these are all the better data for Greenhorn Mountain. And those were all higher angles than even the flat Earth was expected, higher by about 15 or 16 arc minutes, which equates to like about 2,000 feet extra elevation. So when I was looking at all of this, trying to figure out, what's going on, it prompted me to figure out what was going on and to test whether a perfect globe match could be achieved. So I went to a beautiful little spot. Let's see if I can share my Google Earth.
Is that a different window?
Yeah, it'll be a different window, and I'm just sizing it to match and make sure I don't have any doxiferous stuff showing on it. Okay, I just hit the new share and it lets me choose a new thing. Okay, share. You should see Google Earth.
Yep.
So I live between Sequim and Port Angeles, so this is a really nice place. There's a Coast Guard base out here. I think I Googled it. I think like 100 people live out here in the Coast Guard. And they got their, little mini airport and a runway. And their helipads and some big Coast Guard boats and all that stuff. But you can't get onto the end without a pass. But all the way up to about probably right up to about here is, oh yeah, this dock is free public access. Oh, okay, the guard tower is right here. Anyway, this is the fence and the gate. So all the way up to here is public access, and they've got public bathrooms right here, and there's a boat launch, and it's a super, super nice place to go because you can look out north and you're looking out on the crashing waves of the Strait of Juan de Fuca, looking up at Canada. Or inside is a very calm bay where I used to go fishing from an inner tube when I was a kid. So inside here, there's like this little protected harbor inside here. So this is where I went. There's this little pull out right along here. And I set up my telescope with the night vision and the GoPro all like kludged together. And the shortwave receiver playing out the Fort Collins atomic time broadcast. And I had it pointed at this little Blinn Mountain thing or whatever it's called. Somewhere in there. We're getting close. There we go. Which, as you can see, has all kinds of radio towers on it. And it's in the FCC database, so the coordinates and the elevation and stuff are pretty well documented. And I think Dr. Heffron did mention some of the noise or the variation. the stars were being occluded kind of along this little ridge here. They didn't all hit in the same spot. And so see, it kind of slopes down. So they weren't all occluded at the same height. And I did my best to get the elevation of the actual spot where they were included, more or less. But there's also trees that probably stick up, I'm guessing, about 50 feet, which is not reflected in the elevation indicated by Google Earth at different locations. So a little bit of noise would be expected, but the noise was far less than the disparity or the discrepancy between my results and the flat Earth prediction. So let me go back to my spreadsheet, new share, and spreadsheet. I think this is it. Okay. Does the spreadsheet show?
Yep.
Yes.
Oh, good. Okay, so I actually did two sightings or recordings from two locations. One was along the old Olympic Highway at 13.7 miles distance. Those gave a small globe, so they were like 3 to 9 arc minutes below, smaller than the globe prediction. But the one that was the closest was the longer one at 25.4 miles. That was from the Edis Hook that I just showed you on the Google Earth. And I analyzed, let's see, 7 stars from that one. There might be more, but I just ran out of patience and looking for stars in the video. And so these are my times and my locations. And here's the distances in miles and the altitude, the elevation difference. And so you can see here, like I've got 2051, a 2084 plus 50, because Google Earth said that the elevation was 2084, and then I added on 50 for the trees, and same for there. And then that one's 2021 plus 50. So that's how I came up with those heights. If someone wants to do a better way, they're by all means welcome to. My spreadsheet can be copied and modified to one's heart's content. And then here are the altitude angles derived from stellarium using the method of placing stellarium on the occluding peak, turning off atmosphere, and setting it to the date and time and star name. And here is the difference between the globe Earth prediction and the Heffron method angles. Using the Heffron method, it was an average of about 1.8 arc minutes below the globe prediction, 12.8 arc minutes below the flat Earth prediction, and the standard deviation of the globe of the measurements of the difference from the globe measurements was 1.16 arc minutes. So it's kind of a wide standard distribution, but when the disparity is 12 whole, almost 13 whole arc minutes from the flat Earth prediction, a standard deviation of 1.16 arc minutes isn't that big, really, if that makes sense. And of course, here's the discrepancy from the flat Earth prediction in feet, and it's about 500. So that's kind of a high error. Like, just using standard surveying techniques at that distance with a theodolite or something, you would get probably within 20 feet or 10 feet. So a 500-foot error is pretty large. But anyway, that's my data. And I think that the fact that some locations and situations give so close to the globe. In fact, on the wrong side of the globe. These measurements aren't even between flat and globe. They're below both flat and globe, only slightly below globe. I could have, gotten a little bit closer and then brought it up so it averaged spot on for globe, but it's not like they're even in between. It's on the wrong side of globe from flat Earth. So I think, to me, this really means that the method, as currently described, simply is invalid. It cannot be used to meaningfully determine flat versus globe if it can be used to show flat and globe. Does that sort of make sense?
I see where you're going.
So there, would it be all right for Alan to share my spreadsheet again?
Certainly. Let me stop.
Your spreadsheet is excellent, and I can see you put a lot of work into it. You did a lot of good analysis. I'm more familiar with mine, and I did mine different for a reason, and I'd like to point that out once Alan is able to share it. I want to remind everyone that the goal is to reject the null hypothesis, and for that reason, I never would have even selected to do observations on Blinn Mountain, um, uh, because there's not enough distinction between um, the flat Earth prediction and the globe Earth prediction, and I think that's a little easier to see on my spreadsheet. When I first came up with this concept, I thought the elevation angle alone was going to be enough to do it. And for Pikes Peak, that looked like it was true. On Pikes Peak, there was a clear distinction between flat Earth and globe Earth predictions using only the angle. The very second peak I did was Blodgett Peak. And on that one, it was lower than what flat Earth predicted and higher than what globe Earth predicted. And so we had our first real discrepancy where it wasn't clear which way it was slanting. And that's when I realized you can't really go by the elevation angle that stellarium indicates, because as the angle approaches zero, it gets closer and it gets closer and closer and closer to a zero result. And so to meaningfully know which measurement was closer, that's why I started multiplying the distance by the tangent of the elevation to find out what is the indicated rise of that peak, so that we can see how closely does the height of the peak correspond to what flat Earth predicts versus what globe Earth predicts. And so that's why my spreadsheet is set up to emphasize the indicated height of the peak and then compare them, because as you get closer to zero, and we're expecting the globe Earth elevation to be lower, it tends to make the globe Earth prediction look closer than it actually is. And so I switched to finding out what the height was, just so I know for sure, is it closer to globe or is it closer to flat? And I guess there's a little trouble with the spreadsheet.
Sorry, which section?
We can't see it. We can't see it.
Ooh, okay.
It's the low detail version.
So, all right. So people are wondering. So this is Dr. Mike talking. He is pro flat. He's in the upper right at the moment. Jesse is the top left. Jesse.
I'm
and
right on my screen. You're top left on my screen.
Bottom center is Alan. Wait, hold on. I can rearrange.
Oh, I
There we
don't.
go. There we go. Alan, stop laugh now. Uh,
I'm gonna leave and rejoin real quick. My screen share thing is messed up. Sorry about that. I thought it
Uh,
was working the whole time.
all right.
I'll be right back. Sorry about that.
While
Okay, you have left the meeting. Don't show again. Back to meeting. 1 second, lads. Sorry about that. Exit Zoom. Launch Zoom. Meeting. Hmm.
Working on a
Recording in
master
progress.
of, sorry, Bachelor of Science in Electrical Engineering. I got to my senior year and I was doing so much computer work, I switched my major to Bachelor of Science in Computer Science. And that's what I ultimately got my bachelor's degree in. Because of that particular degree, I got hired by injection research specialists in Colorado Springs to resolve an argument between the electrical engineers and the software engineers, where the electrical engineers were saying the engine controllers weren't working properly because the software is bad. The software engineers were saying the engine controllers aren't working properly because the hardware is bad, and they hired me to settle the argument and tell them which one was right, which one was wrong, and it turned out neither one of them was wrong. They were using a bad equation from the Society of Automotive Engineers, and that led to my one and only patent, 5,113,832, for a method for air density compensation for internal combustion engines. And I described that in my second book, Ramblings of an Old Man, about the scientific method. Chapter 2 of that book kind of describes that whole ordeal, but that left me with a background in hardware and software, with a heavy emphasis on physics, because I came out of high school wanting to be a physicist, and I ultimately switched to electrical engineering and then software engineering in the pursuit of money rather than my prime interest of physics. As many people often do, we get lured by the money. And then I went on to get my master's degree in computer science and my doctorate in computer science. So that's how I came to be where I am. I worked till I was 70 years old, which was about 5 years ago, and that's when I finally retired. And I was in the dog rescue business before then, and my life has still gone to the dogs. So as I think, as Jesse's discovered, Jesse and I email each other quite a bit. And I imagine he gets frustrated from time to time because I'm pretty slow to answer sometimes, and I apologize for that. But the dogs take up an unbelievable amount of time, and they're my prime focus. And I do all the rest of this just in the pursuit of the advancement of science, which I think is the same thing that Jesse and probably most of the audience is after. I think we're all in search of the truth, and as we can see, it gets really complicated. So finally, that the spreadsheet's up, that bottom yellow banner
wait,
is.
we have a
Oh,
question.
go ahead.
Fortran, Cobol, Pascal. Yes, yes, yes. No, no, yes, no, yes.
I have experience in all of those languages, as well as various assembly languages, Modula, Lisp, some languages people have probably never heard of, some
Try
languages
me.
that are classified. I have extensive experience in a lot of languages. My favorite is Python, for those who care. My second favorite is probably Java, and JavaScript is a close second. And as you see in my third book, my third book was the Luminiferous Aether. And in that book, I actually deviated and used Frink, because Frink has the unique characteristic of being able to very accurately account for the units and easily convert from one unit to another. So you'll see my Appendix A in that book is all Frink software. And for anybody who's interested, read the book. But I've also got a GitHub where all that software is published. On GitHub, you can just look up Dr. Mike Heffron, and you'll see one folder in there, the Luminiferous Aether, and in that I have Frink software, JavaScript software, and Python software. And then I've also got some PDFs of a couple of presentations I've given over at Aether Cosmology. So for anybody who's interested, all that stuff is available.
Right.
Any other questions about software or hardware or anything else before I move on?
There might be more later.
Okay, interrupt
asking,
whenever.
So, yeah.
Quick question for you lads. Am I able to share the spreadsheet, or is it backed? What happens?
Yeah, we see it.
Okay, cool.
Yeah, it's good. So in that bottom yellow banner, that's the Blinn Mountain data in my preferred format. I couldn't get frames on from Jesse's video, so I just used the timestamp on the video. I converted to the UTC because for whatever reason, my stellarium was an hour off, and I had to keep reminding myself what UTC should have been. So I apologize for that sudden format change on the time, but that's the reason for that. And then the third and fourth star, I think Jesse had different stars that he hadn't identified, but I could identify these two. So I substituted the two I could identify for the ones he didn't already identify for me. And then the rest of this is in my format only. Although I captured the stellarium elevation angle, I quickly realized I need to view these differences in meters, because when you're converting data where the same angle represents a different height depending on which model you're looking at, there was no reasonable way to just evaluate the angles. It needed to be the angle times the distance to figure out the height, and then evaluate the difference in heights. So that's why I did it this way. So other than that, my spreadsheet, if I didn't make any mistakes, and I won't swear that to that, Jesse sent me this data at least a week ago, maybe 2 weeks ago, and I only found time to look at it like over this past weekend. So I haven't had a lot of time to look at this data, and if I made any mistakes, I apologize. But I think I came basically to the same conclusion Jesse did, that this data for Blinn Mountain, this data is closer to what the flat Earth predicts than what the globe Earth predicts. Oh, sorry, I said that backwards again. My usual bad habit. It's closer to what the globe Earth predicts than what the flat Earth predicts. I don't know why, but I do know that it's got the variation, which I think Jesse's explanation for that is probably a good one. It's a little bit closer than most things we've looked at, and it may be a little bumpier than most things we look at. So maybe that's the entire explanation for the large variance. If you study hypothesis testing, what you'll find is a major debate between different hypothesis testing methodologies, and that's why I tried to leave all this data in pretty much raw forms, so that people who want to have debates about methodology could use their favorite methodology And I just settled on one that was easiest for me, which is look at is this data closer to the globe Earth prediction or to the flat Earth prediction? So I think that's all I wanted to say. I I don't really disagree with Jesse's method of looking at the angles, but I think we glean a lot more useful data by looking at the deviation in meters rather than the deviation in degrees or arc minutes or arc seconds. So with that, I'll stay quiet for a while so somebody else can talk or ask more questions.
So what I would like to try to figure, if we could try to figure this out, is what possible thing could have gone wrong to cause that occlusion time to be off by more than a minute, making it match the globe Earth prediction.
So I do have a gut feeling about that, but I want to preface this with the fact that this is pure speculation. The reason I originally went for really tall mountains is so that I could get a really big difference between the height that a globe Earth would predict versus what a flat Earth would predict. So I was going for maximum detectable difference. And with smaller peaks like this, the difference is not as pronounced. In fact, if you look at my highest flat Earth prediction for Blinn Mountain was -88, and the lowest globe Earth prediction for Blinn Mountain was like -88. So you see those. Oh, whoops! I think I misread. Yeah, the smallest, the lowest globe Earth prediction is -61. So those are only 27 or so meters apart. I like to see a bigger difference than that, especially when the deviation is 38 meters. So the difference between flat and globe is less than the standard deviation. And so I was going to the opposite extreme, minimum standard deviation and maximum difference between flat and globe. So it's really, really clear that this is in a flat Earth camp or a globe Earth camp, or at least you can readily identify that it's closer to one or the other. So
what's your standard
go ahead.
Yeah, what's your standard deviation?
For this, I came up with, and it's here on row 57, row 58, column P, plus or minus 38.6 meters. And the difference between the difference between the max and min of flat versus globe is only 27 meters. So the difference between flat and globe is less than the standard deviation. And it's better to have the difference be much larger than the standard deviation. But like I said, this is speculation. I think we're going to have to dig into this to see if we can find other possible explanations for why for this low mountain, the data is kind of the reverse of what we're seeing everywhere else.
So the stars, the 7 stars that I reported in my spreadsheet only give a 1.16 arc minute standard deviation, which is only 13 meters.
Yeah, now, so note again that I omitted 2 of your stars because they weren't identified, and I didn't know which stars they were, but it was really easy for me to identify 2 other stars. So I substituted those 2 stars I could identify for 2 of yours that I couldn't identify. So maybe that's the whole difference. I don't know.
Are the 2 that you identified the ones that increase that standard deviation so drastically?
I don't know because I couldn't identify your stars. I couldn't look up their elevation in Stellarium, and so I couldn't get numbers. So I substituted 3 Capricorni and SAO 163421. And with those, I could get really good elevations. And so I'm using the elevations that I could easily verify. And so basically, I think what we're going to have to do is we're going to have to examine this data more carefully. And since I first looked at it over the weekend, I didn't have time to do that.
Yeah, unfortunately, this data was not sent to me before the event, so I had no way to check it and see if it was correct.
Alan has a real propensity for releasing my stuff before anybody's had a chance to review it, which is okay. I love Alan, and it kind of puts me on the spot and makes me put my money where my mouth is, I guess, and admit to what I know and what I don't know, which every good scientist should always admit to what they know and what they don't know.
So
And
which ones of these on the spreadsheet are from stars that I identified?
it's Rose. The first two and the last one are stars you identify. Only the third and fourth stars are stars that you didn't tell me which stars they were, so I substitute stars that I could identify.
I'm curious what your standard deviation would be on just the stars that I identified.
So on yours, did you calculate the delta between in meters? Well, you use feet instead of oh yeah, so that's another difference, I guess. I'm expressing the standard deviation in meters, and I think you express the standard deviation in feet.
In
Um, oh, sorry, what'd you say?
In arc minutes.
Oh, in arc minutes. Okay.
Yeah, because the distance, all 7 stars were, done between the same 2 points. The distance was 25.4 miles for all 7 of them. So the angle should be, the displacement of the angle is going to be relate the same to elevation because it's the same distance.
So I would urge everybody who's serious about this is do not use arc minutes. Do not use, well, seconds is, I'd say don't even use seconds, use meters. And the reason you want to use meters is arc minutes doesn't translate to the same height on globe as it does versus flat. And if you're looking at what is the real discrepancy, you have to measure that discrepancy in meters, not in arc minutes, because as the arc minutes approach 0, the delta you're looking at is approaching 0. And instead of minimizing the difference, we should be maximizing the difference between globe and Earth, globe and flat Earth predictions.
Well, can't we just take the tangent of the standard deviation and multiply or feed it and multiply it times 25.4 miles and display that in meters? I mean, that's my, if my standard deviation at 25.4 miles is 1.16 arc seconds. Hold on, I think I put, hold on.
Well, if you don't mind me talking while you're looking,
Go for it.
The reason I put the average and the standard deviation on here is eventually at some point in hypothesis testing, usually you want to start factoring the mean and the sample deviation into your calculations. And so the mean and the sample deviation can only be meaningful when expressed as meters, and it can never be meaningful when expressed as arc minutes or seconds. And so that's why I'm trying to gravitate everybody toward expressing everything as what does this represent in actual elevation of that peak in meters, and the difference in meters, and not on the sliding scale of arc minutes or seconds. And I'll mute my mic and be quiet while you resume your train of thought.
I was thinking of, if you want to talk a little bit more, I will go ahead and create the error, an error column in meters and a standard deviation in meters. How does that sound?
Okay, that's great. And I apologize for people who don't like meters. In both of my most recent two books, I express everything as meters, and I explain in the preface why I do that. And that's also why I use the Frank programming language in my third book, the most recent one about the luminiferous ether, because in meters it it helps prevent the mistakes we so often make when we're converting things between um, systems that like use 12 inches to a foot and 3 foot to a yard and uh, uh, 1,260 yards to a mile and all that kind of stuff. If I pull that number out of my head and that might be wrong, but um,
Are you
it
are you contrasting meters uh like between imperial and metric, or are you contrasting between meters and angle measurements?
so I'm contrasting meters, which is a coherent decimal system, to all of the other systems, potential systems of measurement that um, use weird ratios that have to be converted to meaningfully compare things. Meters, the kilogram meter second system allows you to compare things directly. And then also in the book on the luminiferous ether, you'll see that I was frequently comparing my data to the National Institute of Standards and Technology data, and theirs is all expressed in meter kilogram seconds. So rather than converting everything all over the place, I just stuck with the metric system, which tends to minimize the errors and
Yeah, you don't
maximize
need
the
to,
coherence.
yeah, you don't need to apologize for using metric system or SI units. Um, that that should be the default in science.
Well, I like to apologize to anybody who's offended by anything I say. I try not to
Oh,
be offensive, and I know we all try and fail at times, but I think we all make much more progress if we can be polite and try not to offend each other.
yeah. Now, there is an alternative to imperial and metric. That would be sheep units, where everything is derived from sheep. So length is expressed in sheep lengths. Um, weight is expressed in sheep. How much this particular sheep weighed on a particular day. Things like that. Pretty normal stuff that the Scots do for their measurement units. You should look it up. It's just mctoon.net/sheep. I have it all defined there.
I think I may have seen that. I've explored your site and I've read a lot of your stuff. Um, and as soon as the National Institute of Standards and Technology converts to sheep units, I'll happily follow the rest of the sheep.
It's eminent. It's eminent.
All right, I'll watch for that.
Yep. Uh, Jesse, how you doing? We got some questions.
Yeah,
Maybe
I
if
think
you.
I'm almost there. Give me
All right.
another couple minutes.
All right. Um.
I had I had originally done the units in arc minutes because that's how he had done them in his at the time.
Uh-huh.
So I did not know that we would be converting units mid-show.
All right. So Sea Lion Prime asks, Dr. Heffron, what's the point of a null hypothesis without a parameter or test statistic to test against? What is the p-value?
So I think that's a point well taken. Um, uh, and depending on which hypothesis testing philosophy you use, there may or may not be a point. Um, as you can see from my spreadsheet, I am set up to go to t-tests or p-tests or z-tests when we attain enough data to switch to that methodology. Right now, I don't think we know enough to take that step. And and then even within those methodologies, some people advocate for. Oops, hopefully the noise canceling microphone is canceling the robot noise behind me, but uh, and the robot threw off my own train of thought, so sorry about that. Some people in hypothesis testing advocate for throwing away the highest and lowest outlier, which in our case that would be Greenhorn Mountain and Blinn Mountain, which are both marked yellow on this spreadsheet. So those would be the candidates for people who want to throw out the extremes and use just the middle data.
Or if you were me, you could just take my globe matching one and throw out the stuff that was outliers from it. Because I can get a lot more globe ones. I know how to do it.
When we finally reach the actual hypothesis testing stage, I think then you'll probably have everybody on for a new debate about what's the best hypothesis testing philosophy, because it seems like there's a million of them out there.
All right, Mr. Toffees says hashtag real top winner 2025 MC2 and real top winner 2025. He thinks that he agrees with me that the top left voting was rigged. It was completely rigged. Let's see. Bob is.
I don't think I understood that. The top left what?
Top left is an annual competition, and for some reason I got nominated, and the voting was completely rigged.
So is that a cruel comment directed at you?
Yeah, they're poking at me.
You're taking that like a man. Well done.
I am ready.
Okay. Let's see it. Share your screen.
Okay, is it popping up?
I see it.
Yep.
Is it the whole screen or just the spreadsheet?
I see just the window. So there's
okay,
tab.
good.
We see the tabs.
Oh, good. Okay. All right. So I have now. This is just the. Well, better make sure I did it to the right mountain. Yep, it is hooked to Blinn Mountain. But I have created a globe Earth delta in meters and a flat Earth delta in meters. I've taken the averages of those, and I've taken the standard deviation of those. So you can see that the average globe Earth delta is minus 19 meters. So using the method to determine the height of that mountain, I got 19 meters lower than the globe Earth predicted. I got 140, almost 150 meters below what flat Earth predicted. And my standard deviation is almost 14 meters. So a standard deviation of 14 meters is less than 10% of 150 meters. So that's a large, that's a narrow enough standard distribution, far enough from the flat Earth prediction that I don't think we can just say, oh, 25 miles was just too close, and it was random noise. I don't think we can say that, especially considering when we realize that for me to have gotten these readings, the star had to occlude more than a minute in time different than it would have for a flat Earth prediction, right? So that's what I want to understand is what possibly could have actually gone wrong. I mean, that would have caused the star occlusion to happen. Well, my stars were rising, but it appeared more than a minute sooner than the flat Earth model would have predicted, right? And how is that possible? I was super careful with timing. It appeared, most of them appeared very quickly and very brightly, without any question that that's when they appeared. And because of the night vision allowed us to see the skyline of the mountain throughout the measurement, we know that it wasn't just a cloud or something, and that couldn't have made it appear too soon anyway. So is there any known physics that would have allowed this to happen on a flat Earth if this method is valid? Does that make sense?
Yeah.
Yeah, so I'm wondering how you got the elevation for stars you couldn't identify. Um, but um, uh, I think there's a misstatement that the method is invalid because we have outliers. Outliers are normal in scientific inquiry, and I think we still have to um, ask ourselves what's accounting for this discrepancy. Why is this result for Blinn Mountain so radically different than the result for all the other mountains? As you say, I don't think it's because the stars are rising rather than setting. In theory, that should be just as acceptable a way to determine when the star is occluded versus when it's not. Um, I I've heard other theories of of what may account for that, and I don't know if Alan has anybody lined up to discuss any of those theories or not. I don't know if we're at a point where we can discuss that, but I think this is something we have to definitely look into. Why does Blinn Mountain produce results so radically different than all the other mountains? So we are looking east instead of west or south. More importantly, we're looking at stars rising instead of stars setting. But I, I, I think we agree that's probably not the difference. Another difference we're looking at is instead of stars at an elevation of thousands of feet, we're looking at stars at sea level. Is that a factor somehow? I think that's something we'll have to investigate. Basically, what I think we're going to have to do is figure out why is this data so different.
Right. If that's the case, if the method cannot be used below a certain elevation, then I have invalidated it for use below a certain elevation.
So there I have to disagree with you because you're missing the concept of null hypothesis and what the null hypothesis is set up to do. The null hypothesis is the opposite of what you believe to be true. And to refute that, you should be able to refute it at various altitudes, not only at sea level. So if you can make it fail consistently at sea level, but you can't make it fail consistently on mountains in general, you've still managed to invalidate the null hypothesis because it is producing a flat Earth result rather than a globe Earth result. And your hypothesis is that it should be a globe result everywhere, not everywhere except sea level.
Well, my contention is, I mean, we can't even test for a hypothesis until we have a test that is coherent, right? Because I mean, I could go, if I didn't have to work or anything, I could go out and start getting I could get more star occlusion videos than you, all closer to the globe. And however many you have, I could get twice as many. Now yours would be the outliers. And I could throw them out and I could declare Earth as a globe. So that's just a silly game that we have. The method has to be, as defined, has to be coherent with itself. It can't, obviously there's it takes a star 1 or 2 seconds to change from full occlusion to no occlusion. There's obviously a 1 or 2 second, source of error of time there. Obviously there's some error in maybe exactly how high we know a mountain is. There might be some error in exactly the timing when we're recording it because maybe, it's within maybe a second of time because that's, it's hard to get it super close. Although I think I got mine within a tenth of a second of time with the WWV there. But Anyway, from Colorado, Fort Collins. Anyway, I agree that there are a list of known sources of randomness, and we do expect outliers within that margin, a couple seconds of timing and a certain amount of mountain elevation difference. But other than that, we do not expect outliers that equate to more than a minute of time error, or 500 feet, or as you would prefer, 150 meters of elevation error. Those outliers are not expected, right? Because there's no known phenomena that would cause them.
So I think you're unwittingly making the case for why the null hypothesis is necessary in the first place, and you just don't realize it. It's been well known for quite a while that you cannot prove a hypothesis. For example, at Blinn Mountain, you may be well able to demonstrate that, oh yeah, the data clearly shows we're on a globe. But if you can't make that same demonstration at my altitude, well, this is specifically why we resort to the null hypothesis. The null hypothesis realizes that there's infinitely many ways to allegedly prove a hypothesis is true. There's only one way to demonstrate that a null hypothesis is false. And so what we want to do is refute the opposite of what we believe. If we can refute that anywhere, sorry, I'm starting to talk backwards again. When you look at the bell curve, we're basically trying to show what we're trying to refute is the outlier. And if we can't show that what we're trying to refute is the outlier, then we're failing. And that's why one popular hypothesis testing methodology is throw out the two extremes, and then look at the data in the middle. Like I said before, we're not at that step yet. We don't have enough data to do that yet. For my doctoral dissertation, I literally had to simulate 3,000 years worth of software projects to collect enough data to reject my null hypothesis that my hypothesis was false. And one mountain is not enough to do that. You have to be able to show that there are enough refutations that yes, you really refuted it, and then you can use the t-test or the p-test or the z-test or your favorite test to quantify what level of confidence you have. For anybody who wants to go to my GitHub site, you'll see that I showed that I demonstrated that the luminiferous ether explains the fundamental constants of physics to a 6 sigma level of confidence. That is way, way, way beyond what is normal in the scientific community. Normally, if you can get a 95% level of confidence, that's enough to get you a doctoral dissertation. For really, really good universities, they may bump that up to you have to be 99% confident.
I have a question.
But if you're 99.99999% confidence, that's way beyond what's expected. Well, we're nowhere near that yet. And we're going to have to collect a lot of data before we get there.
Right. I do have a question though. What makes my two, because I did measurements to that. I did celestial theodolite measurements to that same mountain from 2 different locations, and they were both closer to globe than flat. What makes my 2 measurements the outliers at this point?
Well, as you pointed out, your data does not match flat or globe, it's a little deviant. Now,
None of
all
yours,
of course,
none of yours match
all of
perfectly either.
all of course, right. I was gonna concede that point. So all of the data is not a perfect match. That's why we need to collect enough data that we can quantify what's our level of confidence. Well, Blinn Mountain is not enough to do that, and neither is Greenhorn Mountain. And in the case of Blinn Mountain, we have a radical departure from all of the other mountains we've measured, and I think we really need to get to the bottom of what is causing Blinn Mountain to give the exact opposite results of what all the other mountains give. Every other mountain shows that the calculated height of the mountain is well in excess of what flat Earth would predict, whereas this one's actually pretty close. And in fact, it's a little too low. But so I think we have to look at this and figure out why. And when people start debating about which confidence level methodology we should use, they'll have to argue: do we throw out Greenhorn Mountain and Blinn Mountain, or do we apply a test that factors that in somehow? And there are hypothesis testing methodologies that factor that in.
But so,
but it's a mistake to think you can refute a refutation. What you have to do is refute the null hypothesis, and we're not doing it yet.
but I can refute a method, right? I can demonstrate that.
See, that's where you're not understanding the method, though. The method is a null hypothesis, the exact opposite of what you believe, and you're not refuting the opposite of what you believe.
But like, let's say I had chosen a different way to measure the height of those mountains, and that way was take a dice and take a couple of dice and roll them until I got the number I wanted and say, look, it matches the globe. And you could say, well, that's not a measurement because it doesn't always match a globe. Could you invalidate my method of rolling and cherry picking dice to prove globe or to disprove flat? Either way.
I think you know the answer to that. In that case, that won't support either method.
I can roll it until I get what I want, and then I can present the ones that matched what I wanted, and then I can say, look, I got measurements. Would you have any? Could you invalidate that if you knew that that was my method? Could you invalidate that as being a valid form of measurement?
In hypothesis testing, you have to ask yourself, what is it that you're trying to refute?
Well, could you?
So what is it that you're trying to refute?
Could you answer that one question? We can't have a hypothesis until we have a way to measure. And I'm asking you, if I were using dice and cherry picking the results from rolling dice and then presenting that as measurements, could you invalidate can you think of any way to invalidate my method of using rolling dice and cherry picking the results? How would you invalidate that?
Going back 50 years when I took actually it was over 50 years when I took debate in freshman English class. I don't remember what your
loaded question.
Loaded question. Thank you. I was having trouble deciding whether this was a loaded question or a false dilemma. But yeah, you're presuming a bias in the way you're answering your question, and I think you know the answer, because the answer goes down to, does your method allow you to refute the null hypothesis? That's the question we need to ask. So does assuming the Earth is flat and then refuting that enable us to refute the null hypothesis? Yes, it did, and it didn't. And right off the bat on Pike's Peak, it was not able to refute it. Now we're in the process of gathering data, seeing when we randomly pick mountains and make these measurements, do we see any trends? Do we see any places where we need to fine tune something? And I think we're just not there yet. This method is 17 weeks old. We need to be collecting more data and looking at what refutes the null hypothesis versus what fails to refute the null hypothesis. And then we need to look, after we've ended up with those two buckets, or as you correctly pointed out, I think there's a bucket in between that it doesn't convincingly support or refute either hypothesis. Well, we need to collect enough data that we can see the trends and we can figure out what makes Blinn Mountain different than all the others. What makes Greenhorn Mountain so high for everything? And we just don't have the answer to those questions yet.
Okay. I need an answer to my question. Mr. Toon, can you answer my question? If I were rolling dice and cherry picking the numbers I liked and presenting that as a measurement for, say, globe Earth or flat Earth, whatever, how would you go about invalidating my method of measuring?
Well, yeah, that method, I would just examine the method and say, well, that method doesn't seem to be measuring the thing that you wanted to measure. I don't know. I suppose you also
Would you
could
roll
look
some would you roll some dice yourself and show that you could also get contradicting results?
yeah, that would certainly do it.
Okay.
You could look at the distribution and say, well, it's all over the place. That'd be another thing.
Right. So, yeah. So basically, I can explain all of these measurements or all of these results on a globe Earth, the flat ones, the concave ones, and the one that matched the globe so closely, because I figured out what's really going on. And so I can predict based on the observer location, the mountain location, and the observer height and the mountain height, I can predict what results you're going to get. So I used that to know, I predicted where I needed to go in order to get a globe result. I went there and I got it. So
Real quick, real
are you
quick,
saying,
you were, or real quick though, you were just talking about cherry picking measurements and using that for falsification. It's exactly what you did with the simulator to propose this to create the ideal conditions. That's not.
Well, it's 25 miles away. His closest one was 22 miles, so it's not too close. It's a place that everyone is allowed to go. It's not like it was anything, it's there was nothing about my method, the way I implemented the method, that was not how he described it. So if the method as it's currently described is valid, then I should not have gotten those results. If I got those results, then the method needs a clause that says you cannot do it. It does not work under the following circumstances, right?
Well, thank you for providing the initial measurements to substantiate that. Much appreciated.
Yeah, well, there again, I'd have to say you're unwittingly illustrating why a hypothesis cannot be proven, and instead you need to refute the null hypothesis. Because when you cherry pick the data, you can give the illusion of proving anything.
Right.
When you refute the data, in other words, you're demonstrating that the opposite of what you believe is false. Now you have reason to believe that what you believe is true objectively. So the fact that not every data point necessarily refutes what you believe, that's when you subject it to a t-test or a p-test or a z-test or one of the other tests. But finding a way to make the test fail in no way invalidates the concept of refuting the null hypothesis.
But showing that the method can give contradicts vastly self-contradicting results when being followed to the T shows that the method can give vastly contradicting results when followed to the T, right?
Well, the vastly contradicting results are given. That's why hypotheses cannot be proven. what you're
if I
looking
can,
for is the outliers, and you're not finding an outlier.
so at Mike, so the live chat here is asking quite a bit about whether or not the issue is the methodology, and that the methodology might be the error, not that you know, if you have a flawed methodology, talking about refuting the null hypothesis or those types of things is moot, because the methodology is the problem. You need to make sure the methodology is sound first, and so that's certainly what the live chat here is bringing up quite a bit.
Let me try and put this into perspective for the live chat lads. We have a new tool here, right? We got a new wrench. We're trying to see what size sockets we can use this wrench on, right? So these new measurements where the distance and the height ratio are skewed, right? That's going to cause, like, how is that going to affect it? Well, we saw that the standard deviation gets a little messed up. So we're going through this process here. To throw it out, act like you refuted the whole thing, it's a bit presumptuous, a little hasty, I would say.
Yeah. So I don't know if that really
The methodology
addressed it.
sound, we're figuring out the parameters on which it can be applied.
But how do you know the methodology is sound? Nobody's used this methodology before that I know of.
So let me explain that, because it's actually quite simple how you know the methodology is sound. When your null hypothesis is the Earth is flat, you're basing every part of your methodology on the concept that the Earth is flat, and then you're trying to refute that. So I took a random example. Pikes Peak was the most prominent, easiest to measure peak from my house. So I started with that. I made the assumption I am on a level plane that intersects Pikes Peak, and so I can take the tangent of the height of that peak above the plane divided by the distance to that peak. That gives me an angle I should expect if the Earth were flat. And that angle is about 2.5 degrees. As I recall, the globe Earth predicts that angle would be 2.25 degrees. So it's about a 1/4 degree difference, if I'm remembering those numbers correctly. So
And this was the one where you used an actual theodolite to measure the angle?
no. This is a plane trigonometry calculation. What so many people refer to as the Heffron angle is actually just plane trigonometry. Now,
okay, but how was this measured then? That's the methodology question, right?
Right, and this is the second part of the methodology. So remember what we are trying to refute. We're trying to refute the contention that the Earth is flat. So if the Earth is flat, then it's flat on the peak too. So we should measure at the time the peak occludes a star. We should see that star at the same elevation on the peak. And part of this methodology is we acknowledge that there is some refraction, but what we're saying is the refraction appears to be a couple of arc minutes at most, and we're talking about terrestrial refraction, not celestial refraction. So we should be able to use the true elevation of that star, and we should be able to refute the fact that the Earth is flat, because that elevation won't equal the elevation the flat Earth predicted. The problem is we couldn't refute that because it was only
the question.
2 arc minutes difference.
You said that the true elevation. When you say true elevation, what is that?
That's where the star actually is versus where it appears to be.
Okay, and so you're comparing where it appears to be with the non-refracted position. Is that right?
No, no. The whole premise of this is where the star appears to be is the whole point of contention when it gets down to it between the flat Earth perspective and the globe Earth perspective. To come up with a globe Earth perspective, you have to argue that where the star appears to be matters, the temperature matters, the pressure matters. The flat Earth perspective says none of that matters to a significant enough degree that I'll measure the flat Earth angle versus the globe Earth angle. So if the Earth is flat, I should measure approximately the flat Earth angle. As if the Earth is a globe, I should measure approximately the globe Earth angle. But what I'm trying to do is I'm trying to refute the fact. I'm not trying to prove that the Earth is a globe. I'm trying to refute the fact.
Okay, but I want
that the Earth
to.
is flat.
You said that. Hold on. That's why it goes back to everybody's wondering about where is the the theodolite, the actual physical theodolite that's measuring the angles. How did you measure the angles?
I got you.
You keep talking about these angles and where it should appear to be, but it's very, very not clear how you're doing that.
Can you hear me?
Yeah.
So that is done through timing intervals, right? So when we know where the star is at with time, so when it's at that specific angle at that time, that's what we're comparing it to. Astronomy is based off of timing intervals. GPS is based off timing intervals. Timing intervals is a perfectly valid method for the application and what we're using.
Okay. And when you did that, when you say we know its position, did you include the effects of the air or not?
That isn't our premise. Our premise is the true geometric position. Where the star is doesn't matter. Like all we're concerned with that true geometric angle and the time that we no longer see it. If those two match up, then we're good to go.
Okay, so how did you measure the true geometric angle?
Reference the almanac.
I mean, no, you don't measure by looking it up in the almanac. How did you measure it?
That's exactly what you do in Stellarium when you turn refraction off. It references the star's true geometric position, which is just geocentric coordinates, just taking a zenith measurement and assuming no refraction, etc. So
yeah, let me ask again. How in meat space did you measure the angle?
Oh, I already answered it. It's through timing intervals. If you disagree with timing intervals, then you disagree with astronomy and GPS, etc.
Just saying timing intervals doesn't actually explain how you did it.
Oh, I didn't just say it. I explained it in detail. So it corresponds to the position of the star that we're referencing using our software called Stellarium. That's how. So we know where the true position is with respect to time, and we know the time that we no longer saw it. If those two are the same, then alpha equals alpha, going back to the diagram that I originally showed. So explicitly explained it in detail.
So you assumed in meat space that air doesn't exist.
Nope, did not assume that at all. I assume that when we no longer see a star, it's no longer refracted. If that angle corresponds to the mountain peak, then that physical object blocked it. That's it.
Yeah, sounds like you're neglecting the effects of the air.
Well, it may sound like one thing, but I explicitly described how it's not. Why would you refract something that you can't see? That doesn't make any sense. If the refraction angle is 0, it's no longer refracted. What are you trying to refract?
The intersecting angle of where the star is and where the peak of the mountain is, both of those are through the air. So you need to include the effects of the air.
Through which we're no longer seeing the star, so what's happening behind the mountain peaks are relevant to us.
Until that goes away.
So between
until the moment that you can't see it, you still need to take that into account.
And the only time we record anything is when we can't see it, so that's why we don't do that. You understand that?
Yeah, that makes no sense at all, though.
What about in my case? I recorded when I started to see them, which was less than a second before I could not see them. I'm
glad you brought that up. So we were thinking of a way to standardize the interpretation of star rises, because we don't contest that a star rise is equally as valid as the star set, but the distinction there is clearly when there's no light there. So when you get into the different ways that you could observe the star optically, so you were using night vision, we don't know how that would amplify the effect of when you first kind of see the star, how that's going to make it look brighter. Is it actually there yet? Is it actually at that position, or does it appear to be because of the amplification of the device? So I was thinking we should discuss that, so whenever you want to discuss how we can come up with a standardized way to interpret this timing for star rises, I mean, I'm all ears.
The amplification of the night vision was about equal to the 1 second exposures of Dr. Heffron's telescope.
Okay, perfect then.
I do
Then-
have something more I would like to go over to when it's my turn.
Oh, you're good. You could speak. But yeah, if it was the same, if it's about the same as that, then like, yeah, we're pretty good to go on that then. So you do it as soon as you can see it then? Or like 1 second after? Is that what you said?
Because mine was recording at 30 frames a second, you can frame forward and back with the arrow key, with the right and left, the greater than, less than, or comma period on your keyboard. And you can either do it when it's half brightness or just before you can first see it, or when it's full bright. You can pick any, but it's all within about a second's worth of time. And it doesn't,
yeah, that's fine then.
it doesn't really change the readings much. 1 second of time difference doesn't change much. But anyway,
Right.
I can explain why we get all the angles we do using the Heffron method on a globe Earth. And this explains how I knew where I needed to go to get a globe-centric result, or a flat Earth, or even a concave-centric, matching result if I wanted to. So I got is my screen share showing?
Mm-hmm.
Yeah.
Okay, so I have picked Dr. Heffron's best flat Earth data point, Mount Rosa. And so the story is his observatory is represented by the little puppies down here. And this one was based on HD 18290, the star. And Mount Rosa, here's its delta height, 4714. And you can see up here, does my circling show?
Yep.
Okay, at that point in time, Dr. Heffron observed HD 18290 occluding behind Mount Rosa, Mount Rosa. And that was like less than an arc minute, I think, from the flat Earth prediction. So this was I picked his best data point. And now I will demonstrate how even that is perfectly possible and expected if Earth were a globe. So down here in the corner, we've got the observer. And the apparent angle to the mountain is 1 minute 32:20. And at that moment of occlusion, that is also the apparent angle to the star. Now, even on a globe, stars will occlude behind mountains. And even on a globe, stellarium will be able to predict the apparent angle to a star at a certain point in time. So if we take stellarium and put it at the observer's location, put in this date and time, and this star, it will give us, if we turn on refraction, it will give us the predicted apparent angle of 132.20, which is also the globe surveyor's predicted apparent angle to that mountain at that time. So that's all true even on a globe. Now, it's also true on a globe that there will be astronomical refraction. In this case, almost 15 arc minutes, it looks like. So even on a globe, if you turn off refraction in stellarium, the elevation angle given for a star will drop. And in this case, it would drop down to 1 degree, 16 minutes, 51 seconds. Even on a globe, that's how much astronomical refraction would drop that star. Now, even on a globe, and especially on a globe, moving stellarium closer to the star will cause the elevation angle of that star to rise 1 degree per 60 nautical miles. So what we've done here is, on a globe, we've started out at the observer's location. We've shown that the apparent angle is equal to the occlusion angle and that stellarium accurately predicts that. Otherwise, I mean, there'd be no point in having stellarium if it didn't work. And if Earth is a globe, then stellarium works on a globe. So we turn off atmosphere in stellarium at the observer location. It gives 1 minute 16:51, or 1 degree 16 minutes 51 arc seconds. We then move it closer. I think my arrow color is not doing it for us very well. There, we move it closer. We move stellarium to the mountain peak, which is 29.65 miles, which is 25.765 nautical miles. And at the rate of 1 degree per 60 nautical miles, that will raise the apparent angle of the star by 0.429 degrees, which is a rise of 0 degrees, 25 minutes, and 46 seconds. Now, as you may recall, the true angle, the unrefracted angle from the observer location was 1:16:51. So I've copied 1:16:51 to up to here. And now we're going to add this 25 minutes and 46 seconds of arc that result from being 25.765 nautical miles closer. I'm going to add these together, and I'm going to then get 1 minute, or 1 degree, 42 minutes, and 37 arc seconds, as you can see right here, which is within 1 arc second of the angle given by the Heffron method. So this demonstrates that even on a globe Earth, these angles are exactly what we would expect. They are not a measurement of mountain height or true angle to the mountain. They are simply the result of a procedure, and that procedure is a function of these input variables, the distance and the height difference and the amount of astronomical refraction. So
All right.
that's, yeah.
All right, you proved our point there, that the globe exists as a refraction correction called celestial refraction. You move the observer to where he isn't to come up with a discrepancy, right? We never told Stellarium where Mike's house was or where he was observing it from to start with, right? All we have is the raw geometric angle and where it is that corresponds to it at that time. So moving it to a new location doesn't help. That's not what's happening on the other side of the mountain.
So which of my specific claims are you disagreeing with? What's the first?
If I could interject, you're trying to prove your hypothesis. What you're failing to do is you're not refuting the null hypothesis, because without refraction corrections, without all of the arguments you're making, the null hypothesis correctly predicts the elevation of that angle, and you're not refuting that. You're only arguing that if you throw in all kinds of corrections, you can cut off the same angle. You're trying to prove your hypothesis. You are not trying to reject the null hypothesis.
But my claim is a very serious claim. And my claim is that even if Earth were a globe, you could still do the procedure. You could still time the star. You could still set stellarium on the top of the mountain. You could still turn off atmosphere in stellarium. Even if Earth were a globe and the mountain really was dropped down however many feet due to Earth curve, you would still get that ultimate angle of 1 minute 42 minute 1 degree 42 minutes and 36 seconds that matched the flat Earth, even if Earth was a globe. Do you recognize that that's my claim?
You are making the standard claim, which is well known, why you cannot prove a hypothesis, and that's why hypothesis testing instead rejects the exact opposite of what you believe. The problem is you are failing to reject the exact opposite of what you believe. The exact opposite of what you believe comes up with the correct elevation for Mount Rosa without any refraction correction.
And it would, even if Earth was a globe, right? it would still come up with a flat Earth result for Mount Rosa, even if Earth was a globe, right?
Only by
You're
moving the
missing the
observer where
point.
he isn't,
You're
though,
missing the
too.
point.
Like the
What? No, I'm not missing the point. I'm
You are
demonstrating.
missing the point. You're trying to prove the hypothesis. What you need to be doing is rejecting the null hypothesis. The null hypothesis makes a much simpler assumption, and you are failing to refute that. You're just saying, oh, well, my method can do it too. Well, we know your method can do it too, because you'll pick whatever refraction you need to prove your point, but you are failing to reject the opposite point of view, that you don't need any of that to come up with the same height for that mountain.
Okay, let me ask you this. Do you believe that if Earth was a globe, that you would have still gotten this 1 degree, 42 minutes, and 36 seconds of elevation angle to the mountain using your method?
So far, the data does not show that to be true.
Well, I know, but we need to look at.
So we're kind of getting lost in the weeds here. So like, why don't we wrap up on celestial refraction in your simulator, and then we take a couple of questions and we wrap up, because Mike has to take care of businesses. Since we're on refraction and celestial corrections anywhere, and we're moving observers to where they aren't, to substantiate claims, I think we should move on to the simulator real quick. We can get out of here.
Well, how is it moving the stellarium to where the observer isn't when it was where the observer is?
Quote from you. If we move it to the mountain, it would be there, and therefore it's the same if we just add refraction there. We never told stellarium where the observer was, dude. So next question.
Well, I
and
think,
also, not to mention the failure to refute the null hypothesis methodology, right? Like, we're not even speaking the same methodology, so it gets frustrating to like listen to this repetition of like not talking about the same thing. We're like talking past each other at this point. So I think we should move on.
well, this is really important here. This is
well, here's the thing. It's already been addressed,
not
right?
gonna
People,
go away
people can
until
go back and watch it if they need more clarification here, right? There's two separate predictions that happen. They don't make the same prediction. You and Piezo actually went over this together, and there's a 6 arc second discrepancy at the end of the day. So like, it's not even identical anyway, dude. So let's move on to the simulator and celestial refraction, please. Otherwise, we're just going to leave.
Well, this is an extremely important issue.
It sounds like you're going back to the original thing.
Alan, you should let him talk.
I should, but I've heard him repeat it 5 times. We've already answered it. And now we're going to go through another circular rendition, which isn't going to go nowhere. So like.
Well, it sounds to me like you recognize that the method would give flat Earth results even on a globe Earth.
I literally just told you, you and Piezo went over it, and it actually doesn't. So you know it doesn't, and the fact that you're now repeating it as if it does.
Well, I have a little more patience with Jesse, so take a brief break and let me talk to him. Sunset is coming up for me in about 20 minutes, and that's bedtime for the rescue dogs. So I do want to move along, but what I hear what you're saying, Jesse, that you can show that this diagram agrees with what globe Earth advocates believe, and that's all well and good. The problem is, with hypothesis testing, you want to prove that the other point of view is wrong, and that's what you can't do in this case. Now, what we need to collect enough data to show in general, can the simple assumption of flat earthers be proven wrong? And so far, we already know in many cases, you can't refute what they're saying. Their simple tactic keeps giving the same results as globe Earth. And it doesn't matter that you can contort globe Earth to give the same results. They're using a system that doesn't require any of this refraction, any of these angles. They just make a simple trigonometric calculation to determine the height of the peak that's occluding the star, and they're right on or pretty darn close in most cases. Blinn Mountain's an obvious example where their prediction is too low. Greenhorn Mountain is an obvious exception where the prediction is way too high for both globe Earth and flat Earth. But in general, the null hypothesis technique has not been refuted, and that's what we need to address. We need to refute the opposite of what we believe, not keep arguing that what we believe is true. Because we can always argue that our hypothesis is true. The accepted hypothesis testing technique is to demonstrate that the opposite of what we believe, the null hypothesis, is false. And that's what's not happening here, or at least not happening consistently.
So why doesn't my two measurements of Blinn Mountain disprove flat?
And I don't know that we can necessarily say it doesn't disprove it at this point. What we're noticing is you used a radically different method and it gave radically different results. And none of us can explain why these results are so different.
Well, what's the difference in the method? Can you quantify the difference in the method for us?
What Jesse's using night vision, which some people have suggested may be picking up photons long before they appear to the naked eye or to a time-lapse long exposure like we've done in the past. We need to answer the questions: why is Jesse's results so much different than what
but you said
all of the other people have come up with?
Yeah, you said it's drastically different. I don't think anybody thinks that night vision goggles is gonna make a big difference on whether or not something is obstructing something else. I don't think anybody in all of physics, optics, and geometry would ever suggest that. And so I think you have a pretty high bar for suggesting that a night vision would make that kind of difference.
Yeah,
so, but you said, hold on, just
earlier I agreed with
Mike,
you on that very point, that we're not arguing that we don't think it'll give the same results. What we're doing is we're noting all the differences and saying, for some reason, Jesse's data is showing the exact opposite of what all other measurements show. So we have,
you said,
even though we don't think it's that, we have to examine.
Listen, you didn't answer the question though, and the audience is asking this. What is the difference? You said there's a difference between Jesse's method and your method. What is the difference? You said it's drastically different method.
Well, there are many drastic differences. We're using different instruments. We're looking at rising stars instead of falling stars. Where he's making measurements at sea level versus at altitude. There's a lot of things I think we have to look into to see why does Jesse's results why does Jesse obtain the opposite results that all of the other measurements so many people have taken are giving? And that's a serious question we need to look at, and we don't know the answers yet.
All right, I think I do. All right, you were talking about a something simulation.
Yeah, can I screen share real quick? Yeah. The big difference in methodology too is Mike goes for null invalidation, right? Which is following the null hypothesis. Jesse's going for positive affirmation. Real quick.
No, just the raw video and putting the data into the spreadsheet.
Oh, trust me.
What's the difference in the?
Trust me, guys. I heard you guys argue it. I know. You're good. Let me see if I can screen share this. Okay. All right. You guys see the screen?
Not yet. This is gray. We'll see.
It's doing it again.
My mouse, I see.
Did you see it now?
Nope, it's just gray.
I'm going to have to leave and come back.
Are you using the app or the web?
No,
Still-
don't make me say it out loud. It's a Linux issue. I'll be right back.
I'm in Linux. I just use the app, the downloadable app.
I know. I use Wayland though. There's different issues with it.
Oh, that's right. That's right. You did mention that.
One second.
Client
Recording
running
in
on
progress.
Alt F4, and so I hit Alt F4, and there my mail was. And I'm like,
It
that's
worked
fun.
every time.
Yeah.
All right. Sorry
Oh, now-
about that.
There we go.
Sorry about that. Okay. So a greater issue actually came up during looking at the simulator that you made. So when you go through the calculations here and the predictions, etc., right, you get down to here to line 15, which is astronomical refraction, which gives, given by this coefficient here, and we'll get to what these are, how these were derived here in a minute. But more importantly, you're using the flat Earth prediction and then applying celestial refraction coefficients to that flat Earth angle, to that raw flat Earth angle, and it's giving you the correct prediction. Now over here, I've changed the flat Earth prediction to the if you go up here, you have the apparent position. So this is the way you have. This is for the globe. This is the flat Earth prediction minus 8 inches per mile squared for your apparent. So when we switch the angle to what it would be for the globe angle, the celestial refraction actually makes the incorrect prediction here. So we'll look at, there's flat Earth, Control Y, changes it to the apparent. So this is using the globe angle. Now you see this deviation here. I'll scroll up so you can see it. So at the distance that was set on the default there for 22, what do you got it in miles there? So anyway, when it's at 22 miles, the distance here, the deviation comes out to be almost a full arc minute. And as you get further away, that compounding error escalates. So as you move this out, it becomes increasingly inaccurate. So although all these refraction coefficients are derived empirically, meaning there's a set of assumptions that are put in for the input for this so that they can integrate a data set into it, so that they could use an expansion series to create a uniform smooth gradient, a static atmospheric gradient, essentially, to move the stars where they would be based off of their elevation angle if the Earth were a globe. But the thing is, you have to apply a raw flat Earth angle. You can't actually use the globe angle. And that's for, and that isn't just for this, right? This is for like all celestial navigation. So any of these coefficients, so when you apply them, they're all with respect to the raw flat Earth angle.
So I'm not sure what your point is. Are you saying that my predictor does or does not reliably predict the results of the Heffron method?
Oh, no. My contention isn't the celestial refraction correction. I'm just pointing that out, that this is something that I noticed from your simulator, like what the implications are. And then when you trace back what the out, like how they got these coefficients, right? Like nobody observed any of this. This is an output of making observation fit what it has to be to move the star so that they can use it relative to their coordinate system. So this is like, they got all these observations and then they're like, how do we fit this curve for this elevation angle? Well, these are the outputs that they get out of that. Like I said, when you get into the, when you get into the integration and the expansion series that they start off with, but it has to be applied to a flat Earth angle. So just wanted to point that out to you.
So, but you're agreeing that my simulator does reasonably accurately predict what the Heffron angle will be given the observer location and distance and height to the mountain and stuff.
Yeah.
Okay. So how it does that is irrelevant. I'm not presenting it as evidence of globe. It's just a handy tool that tells people where they need to go to get the results they want. And it demonstrates that I do understand what's going on because I am able to predict what Dr. Heffron's method will give even before anyone has gone to that location and done the measurement. In fact, Dr. Heffron, would you be willing to go to a location and do a measurement?
Yeah, real
like,
quick.
can I just finish a sentence?
Yeah, sorry.
That is very likely to give globe results in your area?
So I'd have to say you're still missing the point that the goal of hypothesis testing is not to cherry pick data that proves your hypothesis. It's the goal of hypothesis testing is to refute the null hypothesis. That's what your method is failing to do. You cannot refute the Pikes Peak data. You cannot refute the Mount Rosa data that clearly shows the flat Earth predicts the simple, incredibly simple plane trigonometry flat Earth angle, not the Heffron angle, but plane trigonometry flat Earth angle, is exactly what flat earthers predict, and you're failing to refute that. All you do is keep arguing that, oh, I can cherry pick data and prove my hypothesis. Well, people have known for over a century that yes, you can argue for any hypothesis. That's why geniuses came up with the idea of refuting the null hypothesis instead, and that's what you failed to do.
So it sounds to me like you're unwilling to go to a location and do a measurement that's likely to match the globe. Does that mean you're cherry picking things that you expect to be flat Earth?
Let me see, is this a loaded question, a false dilemma, or what? I'm not sure, but you want to change the argument from hypothesis testing to grandstanding, I guess.
Well, if your method works in your area, then you should be able to go 16 miles from Blodgett Peak and get still flat Earth results. My prediction is if you get 16 miles from Blodgett Peak, you'll get globe Earth results. In fact, Alan, go ahead and drag the distance over to 16 miles, if you would, kindly.
Jesse, what you're arguing is you can cherry pick the data and find things that support the globe Earth hypothesis, but what you're failing to do is refute randomly selected null hypothesis.
Mike, I think what he's doing is he's showing that the methodology is the issue.
Right.
The methodology is never the issue when it comes to refuting a null hypothesis.
The methodology is dictated. Correct.
The methodology is dictated by what flat Earth advocates believe, and they believe that none of your refraction matters, that the distance doesn't matter, and when they randomly select mountains and watch it occluding stars, a very significant number of those so far are failing to refute the null hypothesis. So in other words, they're coming up with the exact angle or within a few arc seconds within the limits of what their accuracy allows. They are coming up with the flat Earth predicted angle, thereby failing to refute the null hypothesis that the Earth is flat. The data is showing, yes, indeed, using simple trigonometry, the Earth appears to be flat. It's not being refuted.
So would you be willing to put your method to the test at 16 miles from Blodgett Peak? Or
the method has already been put to the test all over the world.
But not
you're failing to refute it. You're just cherry picking data that you find exceptions that is not refuting the null hypothesis. If you can contrive data to make a particular methodology fail, that's radically different.
But Mike, moving the location isn't contriving data. That's just selecting a different location. All locations are equally valid, right? If the methodology is good, then all locations will be equally valid, right?
Jesse's having to cherry pick data to make the methodology fail, whereas randomly selected data.
But you're cherry picking data too.
randomly selected data shows that it's agreeing with the flat Earth predictions.
I can get more
It
random.
looks like it looks like you're cherry picking data too, Mike. Since you won't take a random location that he's chosen as 16 miles.
He's done it at
he's not
different
choosing a random
locations like
location.
7 or 8 times now.
He's wanting me to go to a cherry picked location.
Yeah,
we've got lots of people randomly picking locations.
He's exposing the methodology error. That's what he's doing. It's very clear.
Not.
Super clear to the audience here. I mean, the live chat here is like, holy crap, the methodology is the issue. The methodology is bad. And he's showing that you're scared to address that.
The methodology is exactly what flat Earth advocates predict it should be.
But your hypothesis isn't flat Earth. Your hypothesis is globe, right?
We're not trying to
so
prove
the methodology needs to be something that's concurrent with the globe.
The methodology needs to be the opposite of what you believe needs to be refuted, and you are failing to do that. You are just cherry picking data that makes it fail. Randomly selected data, like my 3,000 years of randomly selected software projects, refuted my null hypothesis. You are not refuting the flat earthers' null hypothesis.
Well, Jesse successfully did.
Real quick, can anyone show where Mike cherry picked data, whereas Jesse specifically said, "I designed a simulator to
by refusing to test it in any particular location."
Bro, he literally tested it at random peaks at different.
Every single location should be equally valid, and if he's unwilling to test it at any particular location, that tells us all we need to know.
That's been
the methodology is flawed, and he knows it.
Okay, Tune,
who's failing to test it.
Tune, real quick. How was the place selected for him to go and test the methodology? Was it cherry picked from the simulator? All right. So now that that's cleared up, can anyone substantiate that Mike cherry picked it?
He is now.
He's cherry picking by refusing to test another location.
He may not have prior to.
I looked outside my window.
Now, Jesse,
the peaks that are there.
Jesse, would you be willing to go 16 miles from this mountain peak? And you and I could go there and measure it. How about that?
Yeah, if I was in Colorado, I'd be glad to. But I'm not.
We could take a trip there, Jesse. How about maybe that, or maybe some other location that?
Oh yeah.
I'd love to do something like that.
Visible from your house, Jesse?
Maybe we could do a range of distances from the same peak and see if we get variations or if we get consistency.
That'd be nice. Really cool. That would be nice. And that would be much appreciated if you could do that. But real quick, before we get off into travel plans and such, I wanted to wrap up on the fine point that I was trying to make about the celestial refraction corrections just in general, right? Although, like, I'm not saying Jesse's using celestial refraction corrections, I'm just talking about them in general, right? From what I learned from the simulator, right? Is that these solutions that are given per elevation angle are not general solutions for the phenomenon known as celestial refraction. These are a form fit, right? These are empirically derived to fit a data curve, to make it what it has to be. These coefficients that are the output of that scenario, they're not derived from first principles. They're not something that was derived from analysis and figuring it out. This is fitting a data curve. So anywhere that these are applied to move the star where it isn't, to make the use of the coordinate system, is not, it's not valid, right? It can't be substantiated in any way. It can't be falsified. This is a computational model, right? Based off of a static atmosphere. So I just wanted to let everyone know what the celestial refraction corrections are. And when you go to use this simulator, you use a flat Earth angle, you use the raw trigonometric angle, and then you apply a literal globe correction to it in the form of celestial refraction through all these coefficients. Anyway, that's what I wanted to add to that.
Could I say something?
Absolutely.
Thank you. So the $1 million question for you and Dr. Heffron here is, why did I have to use any refraction math to match the results of Dr. Heffron's method if Dr. Heffron's method is not influenced by refraction? Why could I not have made the simulator to work without referencing two kinds of refraction? That's $1 million question. For my part, the simulator works. It works. That validates it as a simulator of Dr. Heffron's method. because
Yeah.
it does work.
Yeah, you're missing the point though. You're not using the globe to make the prediction. You're using the flat Earth angle and using a computational output that assumes a globe to move the star to where it isn't to make that assessment, right? So that's the distinction there.
Well, that's because
It's
that's
not
hard.
it's not refraction, it's math fraction. It's a computational output.
Yeah, but I couldn't make the simulator work without it.
That's our premise.
That's $1 million.
Your premise is my conclusion yet again.
See, here's the thing. If Earth were flat, and if Dr. Heffron's method were simply measuring the elevation angle to mountains, the simulator would have been so simple. All I would have had to do was take the arctangent of the rise over the run, and that would have matched the Heffron angle. But it didn't, except at certain points where lines crossed in the graph. In order to make the simulator match all of Dr. Heffron's method, as it varied from 2,000 feet too high to tiny globe to concave to whatever, I had to employ those formulas to make it match his method. His method is not strictly measuring the elevation angles to mountains on a flat Earth. Otherwise, I would not have had to employ refraction to simulate his results, right?
That's strictly how he predicts it, right? We're talking about the application of using celestial refraction. You're using a flat Earth angle. That's why it works. Because celestial refraction has nothing to do with refraction. It's a computational output to move the star. That's all. The globe doesn't. The globe doesn't have it. Hold on a second, bud.
Snell's law works.
I'm not contesting
Right?
Snell's law,
These
bro. We're
glasses
talking.
work.
We're talking
the
about
lenses and all the cameras that we're using right now works. These were all computed by people that applied Snell's law to grind these lenses to the correct shape.
I'm so glad you brought that up. That's temperature over pressure. That's Snell's law, bro.
Just a second. Go ahead. Let me finish before you jump in. So when we compute the effects in the air, we're using Snell's law also.
Right. Snell's law is derived off of first principles, temperature over pressure. Do not disagree with refraction. That is a real, actual thing. The application of celestial refraction has nothing to do with temperature over pressure. It is an output from fitting a data curve. That is the huge significant difference there. And in addition to that, to make it work, you have to use the flat Earth angle. So like you talking about Snell's law, slightly different thing than what we're talking about here. We're talking about first principles derivations versus a computational output to fit a model. Why would you ever need to use a flat Earth angle if the Earth is a globe?
I don't know what flat Earth angle you mean. Are you talking
the raw trigonometric angle that Jesse's simulator works on, right? To apply that refraction formula, you have to use the raw trigonometric flat Earth angle. You cannot use the apparent globe angle. If you do, it makes that refraction correction makes the wrong prediction. And as you get further in distance, the error gets bigger and bigger.
Yeah, I'm not sure what you're talking about exactly. I use the
flat
Earth angle in my simulator as a starting point because this involves flat Earth assumptions.
It's not only the starting point; it's exactly so. Think about this, right? You use the flat Earth angle, and then you applied something to it that is derived specifically on the principle that the Earth is a globe. They literally start with the globe radius when they start their integration for their expansion series, right? So they're globed out of their goddamn mind for every distance and elevation radially outward to that 3959 all the way to 20 kilometers out. Now, when you apply that correction, you have to apply it to the raw flat Earth trigonometric angle for it to work and make the correct prediction. That's what I'm trying to tell you. There is a bigger, grander scheme going on within this as well that shows that these celestial refraction corrections only work with respect to a flat baseline.
So I have a question. If I can predict the results of a Heffron method before anyone's measured it in a situation that has not been measured yet for distance and height, if I can accurately, repeatedly predict that before anyone's measured that specific setup, does that indicate that I know something about what's going on that you don't know?
It means that you're using a flat Earth angle, because if you try to use the globe angle, the output would not work. So that's what it means. It means that the angles that you're using, the baseline for that equation to apply and give the relevant change for the star's elevation to be useful for navigation for latitude and longitude, you have to assume a flat baseline. That's what it means.
So if you didn't have access to the code from my simulator, would you be able to predict the results of a Heffron angle that in a new unique location and situation?
Yeah, it would just take me longer. You're not understanding the implication here, right? The globe, if you use that as an input, it's wrong. You have to use flat Earth. Make your simulator work.
So answer this. Should not the Heffron angle simply return the arctangent of the rise over the run to the peak?
And it does. And to make and to make the globe Earth prediction match, you have to use the flat Earth angle to apply the celestial refraction corrections. Do you understand that? That is the whole baseline and premise of this. You keep repeating that and asking it. It's kind of getting annoying.
But it doesn't.
Use the globe then. Use the globe. Use the globe angle.
It was 2,000 feet too high on Greenhorn Mountain. It was halfway between
Did you hear
globe
me? Did you hear me? If you're not going to use the globe angle, you're not saying anything new, and it's just kind of getting annoying. And like I said, me and my boy got a tight time schedule. So if you have nothing new to add to the conversation aside from showing that all these celestial refraction coefficients only work when you apply a flat baseline to them, I think we're wrapped up here, bro. I look forward to your simulator part 2 that uses the globe angle.
The simulator works. It tells us where we need to go to get what we want.
Because it's with respect to a flat baseline, as noted by you in the math in line 15. If you expand out calculations, you will see that the angle that you are applying all the celestial refraction angles to is the raw trigonometric angle.
I think it's just I used that because it was very close and it needed some angle.
No, it's not, because when I changed it, it changes. And then when the distance increases, the deviation becomes even more apparent. So it's not just by convenience or accident, it's purposeful. I literally screen shared it and showed you what the line moving up and down when you change it. So it's not that. It literally only works when you use a flat baseline.
But
that applies outside of even just the the beauty of this is it applies outside of the scope of even the celestial theodolite for the implication.
Well, how it works is irrelevant. The point is
No. It's specifically relevant, Jesse.
Alan, you keep interrupting, Alan. Just let him talk a little more.
I'm so sorry, but McToon, it's literally, if you use the globe angle, it doesn't work. So what the basic premise of what he's about to just start saying, wrong right off the rip, dog. I just showed it.
But you should still let him talk.
You're right. I apologize. Fair enough.
Thank you. So, but you already agreed that my simulator does reasonably match Dr. Heffron's results. Do you also agree that it matches Dr. Heffron's results much more closely than they match the arctangent of the rise over the run?
Why does it reasonably match, Jesse?
Because I figured out what's really going on. I put in what needed to go in to make it work.
And what needed to go in to make it work? What's the angle that you use? What's in line 15? For the celestial refraction corrections. What angle are you applying the coefficient to?
You didn't answer my question.
What angle are you applying the coefficient to, Jesse?
Let me ask Dr.
You
Mike.
figured out what you needed to figure out to make it work, Jesse. What angle?
Dr. Mike, did you get a chance to look at my simulator?
Expose the error in the methodology, Alan, is what he did.
Nah, didn't, bro. If you use the globe angle to the celestial refraction, it doesn't work. This is the same refraction coefficients that are applied for navigation, dude. GG. This expands outside of the scope of even the celestial theodolite. He just said, I figured out how to make it work. I asked him how he figured it out, what he did to make it work. Didn't answer. Asked him to specifically go to line 15 and show me the calculation for the angle that he used to make it work. Says nothing. I pulled it up and screen shared. Everybody here sat here and watched it. You guys all watched the line go back and forth when we changed the angle from globe to flat Earth.
It didn't go back and forth. It didn't go back.
One second. Hold on. Let me screen share.
I said it didn't go back and forth.
No, hold on.
Much. I said much.
And as I was telling you, as you increase with distance, there's a compounding error, dude. That's it.
But the point is,
Nope, that is the point.
Oh,
Your simulator works great with a flat Earth
Okay,
as a
I
baseline.
need to ask Dr. Mike a question. You won't let me ask you a question, Alan, and you won't let me ask him a question. Okay, that doesn't work.
Real quick,
That
can you
doesn't-
just okay, here's the thing. If you want to ask him a question, there's a price to pay. You have to tell me what angle you use to make the prediction for your simulator. Go ahead.
Some damage control there, Alan.
Yeah. You didn't answer my earlier question, so I'm not going to answer that.
I answered it multiple times.
If you want to go over the code sometime,
Your
we
simulator
can.
works great, Jesse. But why?
We-
You said you figured out something. What'd you figure out, bud?
Okay, so the question is,
dog. All right, Mike, we're done here. We could wrap up, dog.
But I'll be happy to answer Jesse's question before I go.
Yeah.
As you can
Alan,
see,
if you have
it's
if you have
getting
a tight
really
schedule,
dark
Alan,
here.
you can go if you need, Alan.
I ain't gonna
You know,
abandon Mike, but
I can only stay around for a few minutes because, as you can see, it's getting really dark here and the dogs have to go to bed. But I heard Jesse's question. I understand Jesse's question. I did see the simulator. Alan is right on. Line 15 uses the flat Earth angle, and it does so because the simulator is specifically appears to be. And I'm not casting any aspersions or making accusations, but it appears designed to find places where real refraction can cause the plane trigonometry flat Earth angle to give different results because of real refraction. And then it's trying to exploit that as if that's a refutation of the concept. And it's ignoring the fact that the whole premise of the rejecting the null hypothesis is not to create a minimal difference like Jesse's simulator is doing, but to create a maximum difference so it's clear whether this is closer to a flat Earth angle or a globe Earth angle. The simulator is not doing that. The simulator is basically telling you where to go so you can make it appear that the flat Earth angle is wrong by circumventing specifically what it was designed to do, which is the opposite of what the simulator is trying to do. The simulator is trying to cherry pick data. The real occlusion measurements are trying to randomly select mountains. In my case, is the mountains right outside my window. Jesse's free to do this with the mountains right outside his window. Many other people have done it with the mountains outside their window. A lot of them have wised up and gone to public places, so that it's harder to pinpoint where they are. But in any case, I personally don't use the simulator because the simulator is designed to cherry pick data, not to scientifically reject the null hypothesis. It's trying to prevent rejection. That's not the scientific method. The scientific method is test the peaks occluding stars wherever they fall and see, can you reject the null hypothesis? What we are finding is in most cases we cannot reject it. And even in spectacular failures like Greenhorn Mountain, where the result is way high, the way high result is much closer to the flat Earth prediction than to the globe Earth prediction. As scientists, we all need to start digging into what precisely is causing these deviations that depend on the distance, that depend on the location, that depend on the altitude. But in general, right now, it looks like the flat earthers have a really good case because they don't need refraction to fail to refute their hypothesis, the null hypothesis. The data seems to show they're right. Unless you use a simulator to cherry pick a location where it fails.
Well, there are like 100 people, Coast Guardsmen, living on that base there, I believe. What if one of them had just randomly seen your video and done that method? That wouldn't be cherry picking because they live there. That's where they live. But they still would have gotten the same globe results, right? I didn't get globe results.
I agree with you completely. I agree with you completely. I don't think you yet understand the concept of refuting the null hypothesis. Even though your data is closer to the globe, it's not refuting the null hypothesis because so many data points agree.
Mike, he's shown that the underlying assumption that the methodology is good is the problem, right? The refuting of the null hypothesis is only valid if the tape measure is correct, and the tape measure is not correct. That's what he's showing.
So I disagree with your portrayal of what he's showing. What he's showing is you can cherry pick certain spots where real refraction, real conditions that we may or may not know what they are, cause the data to deviate for the vast majority of randomly selected locations, that's not the case. So I challenge Jesse to just randomly pick locations in mountains and see if he can refute the null hypothesis with randomly selected peaks and locations, rather than peaks selected by his simulator, which are designed to make the calculations fail.
Or maybe it's designed to make them succeed and Earth is a globe. Maybe I'll get a whole bunch of globe ones and then mine will be in the majority and yours will be the outliers. And
There you go.
we'll switch the null and the main hypothesis.
The
and
popularity wins.
Oh yeah, maybe you use the globe angle in your calculation as well, or I guess you'll just keep using the flat Earth angle masquerading as a globe. You ready to wrap up, Mike? Because these guys are just going to jerk each other off.
I'm ready. It's getting dark here, but I have a suggestion for your next debate: is get a bunch of hypothesis testing experts to debate hypothesis testing methodologies.
So I would like to leave a question in the air since no one wants to answer it. The question is whether the results from the Heffron method are predominantly closer to my simulator's results or closer to the rise over the run or the arctangent of the rise over the run. I
answered it multiple times. Your simulator is better. And I asked why it's better. And then we're talking about the angle that you used to make the prediction for why it's better, Jesse. And then you stopped answering. That's weird. Anyway, okay. We're about to wrap up, bros. Peace.
So if it's better, then what could be possibly better than simply the arctangent of...
All right, lads and ladettes, that is it. All right. Tune into the boys on Discord. Yo, lads, we're still live on Discord.
Oh, bro.
That was interesting.
That was really painful. Oh my God, that guy just kept everyone going in circles.
Had to be done, though.
So basically, just gonna say this. The first, hour and a half, 2 hours of that should have been condensed into maybe 30 minutes. But it was worth it, I think, for that last 10 minutes, because I have not seen Jesse's jaw drop and sit in silence and stunned like that in a long time, and that was hilarious.
Yeah,
but if I apply endless corrections, if I apply a density gradient, a pressure gradient, this other variable, a constant from a curve best fit, another variable over here, then I can make it work. What do you say to that?
The trees too, it makes it even more difficult.
Well, you guys will have to, tomorrow or the next day when you're not tired and it's super late, go back to when you first brought that point up, though, Alan. When you first brought it up, the first time you said it, his face just went oh,
he knows.
It was great. Total clip. Yeah, he clearly knew. That was caught red-handed, dude. He wouldn't even answer you. You'd already said it 5 times, but then when you asked him, he's like, so you're saying it's better? No, but why is it better? What angle did you use as the input? Which angle was it, Jesse? Well, I just want to ask Dr. Michael a question. No, ask. I just want to. Okay, you can ask Dr. Michael a question, but you have to pay the cost of answering my question. Which angle did you use?
Jesse never answers questions, though. We knew that going.
Oh, his face was priceless, Piezo. You are so correct. Just you had him back into the corner. It was he knew it.
That was tasty. Oh man, that was tasty.
Sliced him up good.
So I would totally get a 20-minute, 25-minute condensed recap of all that stuff.
Oh yeah.
For upload to your channel. I mean, I know you got the whole live, but
Yeah.
Let him do his little obfuscation. Make sure you paint it accurately. Don't cherry pick. Let him get his
Bro, I
point
ain't got time for
across.
all
and
that shit. I'll be right back. I'm gonna roll my intro. All right, lads and ladettes. Thank you for tuning in. Keep running like a coward. Dude, Alejandro Vallejo. We all know why the simulator is so accurate now, brother. And we all know why celestial refraction works. Because it's with respect to a flat baseline. That is the broader implication of what was put forward and exposed by that. You guys on Thursday